There's a glowing object passing through our solar system right now, and nobody can agree on what it looks like. NASA's spacecraft sees a pale, shapeless blur. A hobbyist in Scotland with a $1,000 telescope sees a sharp geometric structure with internal brightness patterns, same object, same week, completely different realities. Welcome to the resolution war of 3i Atlas, where the tools we use to see the universe might be lying to us, or finally telling the truth. Are smart telescopes accidentally revealing a plasma boundary that billion-dollar satellites are filtering out? Or are algorithms hallucinating structures that don't exist? Stay with us to the end, because the answer changes everything we thought we knew about observation itself. And it starts with 48 hours in November, when the images stopped making sense. If you're as captivated by this mystery as we are, go ahead and like this video and subscribe so you catch every twist as this story continues to evolve. Leave a comment telling us where you're watching from, what hour it is in your corner of the world, and whether you think the real picture is being shown to us, or if there's more hiding in the data we're not being told about. Part 1. The November shockwave. The week. The images stopped matching. It was 48 hours in late November 2024 when the internet's fragile consensus about interstellar object 3i Atlas shattered like glass. 3 new images dropped within 2 days. Same object, same week, same patch of sky. But they looked like photographs of 3 different worlds. The first came from NASA's Mars Reconnaissance Orbiter, repurposed to track the visitor as it screamed past Earth. What it showed was a pale, diffuse sphere. No edges, no structure, just a ghostly smudge against the darkness, the kind of thing you'd expect from a dirty snowball tumbling through space. Professional, clean, boring. The second came from the Gemini Observatory's raw frame, released without fanfare to a handful of researchers. Slightly elongated, still featureless, but with a hint of something stretching along one axis. Not enough to raise eyebrows, but enough to make you squint and wonder if the blur was real, or just atmospheric noise playing tricks. The third came from everywhere at once. November 24th. Backyard astronomers across 3 continents uploaded their smart telescope stacks to astronomy forums, and what they showed stopped the conversation cold. A sharp, spindle-like geometry, internal brightness gradients, hard edges where there should have been soft glow. It looked engineered. It looked wrong. It looked like someone had swapped in a completely different object. How can the same celestial body appear as a blob, a smudge, and a blade depending on who's looking? This wasn't a matter of resolution or zoom. These were contradictions. And in astronomy, contradictions are either evidence of catastrophic equipment failure or evidence of something nobody wants to say out loud. Within hours, the forums erupted. Instrument specialists began pointing fingers at NASA's imaging pipeline. The accusation was specific and damning. The agency's sodium doublet-rejecting filters, designed to block bright emission lines at 589 nanometers, might be erasing the object's natural glow. Think of it like photographing a neon sign through sunglasses that block exactly the color the sign emits. You'd see darkness where others see light. But here's where it gets technical, and where the technical matters. Narrowband filters aren't some sinister censorship tool. They're standard equipment, used to isolate faint dust reflections from the blinding glare of gas emissions. If you're hunting for the microscopic particles that trail a comet, you need to block out everything else. The sodium line is one of the brightest things in the sky when ionized gas is present, so you filter it out. It's not hiding evidence, it's just selective blindness in the name of clearer data. Except in this case, selective blindness might mean missing the entire point. If 3i Atlas is emitting strongly in sodium wavelengths, and you're filtering those wavelengths out, then your billion-dollar spacecraft is essentially deaf to the object's loudest scream. Meanwhile, consumer-grade telescopes with broad-spectrum sensors are picking up the full choir. And that's not even the strangest part. The strangest part is the consistency. Every single amateur capture on November 24th showed the same structure, same spindle shape, same brightness distribution, same hard-edge geometry. 3 different observers, 3 different continents, Brazil, Canada, Scotland, different hemispheres, different atmospheric conditions, different equipment setups, but the same shape. Coincidences like that don't happen in astrophotography. When multiple independent observers see the same thing, it's usually real. When they all see something professional instruments miss, It's either a mass hallucination or a revolution in how we understand observation itself. The uniformity raised an immediate question. Could this be an error baked into the technology? Smart telescopes use stacking algorithms, live noise removal, and AI-assisted sharpening to pull signal from chaos. Maybe they're all making the same mistake. Maybe the spindle isn't out there. Maybe it's in here, in the code, in the pattern-matching neural networks that guess what edges should look like based on training data. But then you hit the counterpoint. If it's an algorithm error, why does the error produce the same output across different brands of telescope using different software? The Dwarf 3 runs one processing pipeline. Unistellar runs another. Some of the observers on November 24th weren't even using smart scopes. They were using stacked DSLR frames processed manually in open-source software. And they still saw the spindle. So either every piece of consumer astrophotography equipment has the same bug, or they're all detecting the same signal. And if they're detecting signal, then NASA's images aren't just different, they're incomplete. This is the question that fractures the entire debate into two armed camps. On one side, the professionals insist that amateurs are benefiting from lucky atmospheric windows and over-aggressive post-processing. On the other side, the amateurs insist they're seeing the real object, and that institutional imaging pipelines are sanitizing the truth. And in the middle, stuck between condescension and conspiracy, is the uncomfortable possibility that both sides are partially right. That the shape is real, but not solid. That the glow is genuine, but not what we think it is. That 3i Atlas is something we've never seen before, and our instruments are fragmenting it into incompatible realities depending on what wavelengths we allow ourselves to see. Because here's the thing nobody wants to admit. A backyard telescope seeing what a spacecraft cannot isn't just embarrassing, it's destabilizing. It suggests that the most expensive instruments in human history are optimized for the wrong questions. That we built our eyes to see dust and rock, and something made of light and metal just slipped past us. So how do we know what's real? Do we trust the instruments designed by experts, or the accidents stumbled upon by amateurs? Do we trust the algorithm, or do we trust the lens? And if the answer is neither, if the answer is that reality depends on how you look, then what happens when the thing you're looking at doesn't care which tool you're using? What happens when it looks different? Because it is different depending on who's watching. That's not astronomy. That's something else entirely. And the fight over what to call it is just beginning. Part 2. The false sharpening debate goes nuclear. The technical battleground has a name now. It's called the false sharpening debate, and it's tearing the astronomy community into factions that barely speak the same language anymore. At the center of the war is a single question that sounds simple, but cuts to the bone of how we verify anything. Are smart telescopes creating the structure they claim to see, or are they revealing structure that's always been there? Let's start with what the optical engineers are saying, because they're the ones who actually build these devices and know what's happening under the hood. According to forum posts from developers who worked on the Dwarf 3's imaging pipeline, the so-called sharpening feature isn't really sharpening at all. It's a stabilizing deconvolution kernel. That might sound like technobabble, but the distinction matters. A deconvolution kernel doesn't invent detail. It removes blur by mathematically reversing the blurring process. Think of it like unmixing paint. If you know how the colors blended, you can work backwards to separate them again. When a telescope captures an image, atmospheric turbulence, optical imperfections, and sensor noise all blur the incoming light. A deconvolution algorithm tries to undo that blur by identifying repeating patterns and locking onto edges that appear consistently across multiple frames. This is not the same as a smartphone camera's beauty filter. A beauty filter guesses what you want to see and imposes it on reality. A deconvolution kernel looks for what's actually there and tries to clean off the mud. The difference is intent. One creates, the other clarifies. And here's the key insight the engineers keep hammering home. If the algorithm is creating false structure, it should create different false structures depending on the noise profile of each observation. Random artifacts shouldn't align across independent captures, but the spindle shape does align. Night after night, observer after observer, the same geometry emerges. That consistency is the smoking gun suggesting the algorithm is stabilizing real features, not hallucinating imaginary ones, but the professionals aren't buying it. NASA and JPL insiders, speaking anonymously on imaging science forums, argue that amateurs are benefiting from lucky imaging. This is a real phenomenon. Atmospheric turbulence isn't constant, it fluctuates. For brief moments, sometimes only a few seconds long, the atmosphere settles into an almost perfect window of clarity. If you're taking hundreds of short exposures and stacking only the sharpest ones, you're effectively cherry-picking those lucky moments and compounding their clarity. In other words, the amateurs aren't seeing better because their tools are better. They're seeing better because they're taking so many shots that a few of them happen to catch the atmosphere behaving itself. Professional observatories, by contrast, often take longer single exposures, optimized for faint object detection, not edge resolution. They're playing a different game with different rules. So far, so reasonable. Except there's a third layer to this, and it's where the debate turns radioactive. Alleged leaked flow diagrams started circulating online earlier this year, claiming to show NASA's multi-stage image cleaning pipeline. These diagrams, if real, depict a process where raw data is passed through bias correction, flat fielding, cosmic ray rejection, background subtraction, and then a Gaussian smoothing pass before release. Gaussian smoothing is a fancy term for controlled blurring. It reduces noise, yes, but it also erases fine detail. If you're smoothing an image before the public sees it, you're making an editorial choice about what constitutes signal versus noise. And if the thing you're imaging happens to have faint plasma structures or edge-like boundaries, smoothing will delete them. Now let's be clear, these diagrams are speculative. No one has confirmed their authenticity. They could be fabrications designed to stoke distrust. But the existence of the speculation itself reveals something important. There's a widespread belief, fair or not, that institutional pipelines prioritize safety over fidelity, that agencies would rather release a clean, uncontroversial image than a messy, confusing one. And that belief isn't baseless. Image processing pipelines do delay data. They do apply cleaning stages. This is standard practice, not conspiracy. But standard practice starts to look suspicious when amateur data consistently shows structure that official data does not. If you're a backyard astronomer and you're seeing a spindle and NASA is releasing a blob, you're going to wonder what's happening between the sensor and the press release. The professionals respond by pointing out that amateurs often overprocess their images. They crank contrast, boost saturation, apply unsharp masking until noise starts looking like features. And sometimes it is just noise. Sometimes people see patterns in static because our brains are wired to find faces in clouds and meaning in chaos. But the engineers fire back with math. They point to signal-to-noise ratio calculations. They show that the spindle's brightness gradient follows a predictable curve, not the random spikes you'd expect from noise. They demonstrate that the structure persists across different stacking methods, different software packages, different cameras. They argue that if it walks like a duck and quacks like a duck across a dozen independent detection methods, maybe it's a duck. And so the debate spirals. Each side has data, each side has expertise, each side has reasons to distrust the other. The professionals think the amateurs are naive, the amateurs think the professionals are arrogant, and the public, watching from the sidelines, starts to wonder if maybe the truth isn't on either side. Maybe the truth is that both tools are showing partial realities, and the full picture requires admitting that no single instrument has a monopoly on seeing clearly. Because here's the uncomfortable thought creeping into the conversation. What if 3i Atlas is genuinely ambiguous? What if it exists at the boundary between solid and plasma, between object and field, in a state that looks different depending on what wavelengths and exposure strategies you use? What if the reason the images don't match is because the thing itself doesn't have a single stable appearance? That would mean the fight isn't about who's right. It's about what questions we're willing to ask, and whether we're ready to accept that some objects might not fit the categories we built our instruments around. Which brings us to the next fracture point in this story, the missing tail that should be there but isn't, or maybe is there, but only if you know how to look. Part 3. The missing tail revisited, now a forensic problem. Comets are supposed to have tails. It's the defining feature. A comet without a tail is like a bird without wings. Technically possible, but so rare it demands explanation. And 3i Atlas, by all accounts, is almost tailless. This puts it in a strange category called Manx comets, named after the tailless cat breed. These objects exist, but they're not well understood, and they make professional astronomers nervous because they break the standard playbook. NASA's instruments are optimized for dust. Dust reflects sunlight. Dust scatters predictably. Dust creates those iconic sweeping tails we associate with comets. The entire imaging pipeline is built around detecting and measuring microscopic particles trailing behind a nucleus. So when an object shows up with barely any dust emission, the instruments struggle, they underexpose, they produce fuzzy, low-contrast images, they see almost nothing, and that's exactly what happened with the official images of 3i Atlas. Pale, faint, structureless. The kind of image that makes a press release boring and makes scientists shrug. Low-activity object. Not much to see here. Move along. But between November the 22nd and 25th, something strange started showing up in backyard data. Amateurs with consumer-grade spectrographs, the kind of equipment you can order online for the price of a used car, began detecting strong sodium emission spikes. Not faint traces, strong repeating pulses in the 589 nanometer line. The signature of ionized sodium glowing under solar wind bombardment. Sodium emissions are not subtle. When present, they light up broad-spectrum sensors like a neon sign. And that's exactly what consumer RGB cameras were picking up. A glowing halo, a diffuse shell of light. Not a dust tail, but a gas tail, or something in between. Something that didn't fit the comet model, but definitely wasn't nothing. Contrast this with NASA's official statements: low gas activity, minimal outgassing, inactive nucleus. If you only read the press releases, you'd think 3i Atlas was a dead rock drifting silently through the solar system. But if you looked at the amateur spectrographs, you'd think it was a fireworks display. So which one is true? The answer, frustratingly, is probably both. And that's where the Manx Plus hypothesis comes in. This is the idea currently gaining traction among independent researchers who are trying to reconcile the contradictions. What if 3i Atlas isn't emitting much dust but is heavily emitting metal ions? Nickel, iron, sodium, elements that glow brightly when ionized but don't produce the kind of reflective particle clouds that dust-focused instruments are designed to see. If that's true, then the object would appear dead through NASA's narrowband dust filters. No particles, no signal, but it would appear brilliantly alive through consumer RGB sensors that capture the full visible spectrum, including the bright emission lines where sodium and other metals radiate. It's not that one side is wrong, it's that they're looking at different aspects of the same phenomenon. This isn't just a technical dispute anymore, it's a forensic investigation. Because if 3i Atlas is metal-rich, that raises immediate questions. Where did it come from? Typical solar system comets are ice and rock with trace metals. Interstellar comets could have different compositions formed in environments we've never sampled. But a metal-rich object glowing with ionized sodium? That's exotic. That's the kind of composition you'd expect from something that melted, cooled, and reformed in conditions unlike anything in our neighborhood. And it gets weirder. Some researchers have pointed out that the sodium spikes detected by amateurs don't follow the smooth decline curve you'd expect from outgassing. They pulse, they fluctuate, they appear and disappear over timescales of hours. That's not how passive gas emission works. Passive outgassing is steady, predictable, driven by solar heating. Pulsing emission suggests something more dynamic. Active processes, electric fields, plasma interactions. But here's where skepticism enters the room. Sodium contamination is a real problem in amateur spectroscopy. Earth's atmosphere is full of sodium. Streetlights emit sodium. Even the human body sheds trace sodium vapor. If you're not carefully calibrating your equipment and subtracting atmospheric contributions, you can easily mistake local contamination for signal from your target. It's the oldest mistake in backyard astronomy. So are the sodium spikes real, or are they artifacts? The truth is, we don't know for certain. Some observations included careful atmospheric baseline measurements and still detected the signal. Others did not. The data is messy, contradictory, and incomplete, which is exactly why this has become a forensic problem. We're not just asking what the object is. We're asking whether our tools are capable of telling us the truth and whether we're capable of recognizing it when we see it. Because at the end of the day, a tailless comet that glows without dust is an oxymoron. It shouldn't exist. But it does, or it appears to, and whether that appearance is physics or artifact depends entirely on how much you trust the instruments doing the looking. And trust, as we're learning, is in short supply, which brings us to the next problem. The repeating structure that appears again and again, no matter who's looking or when they look. A pattern so consistent it's either proof of reality or proof that everyone is making the exact same mistake. Part 4. The repeating structure. Mystery. Let's talk about triangulation. Not the mathematical kind, though that's part of it. The observational kind. The kind where multiple people in different places see the same thing, and you start to believe it's not just in your head. Because belief in astronomy isn't about faith, it's about verification. And when 3 observers separated by thousands of miles all capture the same geometry, something real is happening. Brazil, Canada, Scotland, November 24th through 26th. 3 amateur astronomers, working independently with no coordination or communication during their observation windows, uploaded processed images of 3i Atlas to public forums. And when the community overlaid those images for comparison, something impossible happened. They matched, not approximately, precisely. The same spindle-like structure, the same internal brightness gradients, the same hard-edged boundaries where soft glow should have been. Now, you might think matching images from different locations isn't surprising. After all, they're looking at the same object. But in astrophotography, especially of faint, fast-moving targets, perfect agreement is rare. Atmospheric distortion varies by location. Equipment sensitivity differs. Processing choices create divergence. Normally, when multiple observers image the same object, you see the same general form but with individual quirks, slight rotations, different noise patterns, variations in contrast and edge definition. What you don't see is pixel-level agreement on structural features, and yet that's exactly what happened. Each observer used different tracking speeds to compensate for the object's motion across the sky. And here's the critical detail. If the structure were an artifact of motion blur or tracking error, it would change depending on how fast the telescope was slewing. A smear caused by movement is directional. It stretches in the direction of motion. But the star fields in each image remained pinpoint sharp. No trailing, no elongation. The tracking was accurate, which means the spindle shape wasn't a smear, it was the object, or rather it was something around the object. Because this is where the alternative explanation starts to take hold, and it's an explanation that makes both sides uncomfortable for different reasons. What if amateurs aren't imaging the physical nucleus of 3i Atlas at all? What if they're imaging the plasma boundary? A plasma boundary is the edge where the object's local environment meets the solar wind. Think of it as the bow shock, the place where charged particles flowing from the sun collide with charged particles flowing off the object. In that collision zone, energy concentrates, temperatures spike, emission intensifies. If you're looking at a comet or asteroid with broad-spectrum sensors, you might see that boundary as a sharp-edged glow, even if the nucleus itself is faint or invisible. This is where stacking algorithms become both a blessing and a curse. Stacking takes dozens or hundreds of images and aligns them to build signal out of noise. But it also enhances edges. If there's a soft gradient between bright and dark regions, stacking can sharpen that gradient into what looks like a solid line. It's not creating the gradient out of nothing, but it is making it appear more defined than it really is. A plasma boundary, which in reality might be a fuzzy, fluctuating zone of ionized gas, could be rendered as a hard geometric shell after stacking. And that would explain everything. The consistency, the geometry, the sharpness. Plasma boundaries are physical structures governed by electromagnetic forces. They're not random, they're shaped by the interaction between solar wind and the object's magnetic or electric field. If 3i Atlas has a strong field, or if it's shedding ionized material, the plasma boundary could be stable and symmetric. And if it's stable and symmetric, multiple observers would see the same shape, because they're all imaging the same electromagnetic structure. But here's the problem with that explanation. NASA's instruments should see plasma boundaries too. In fact, they're often better at it. Professional spectrographs can isolate emission lines from ionized gas with precision amateurs can't match. If there's a glowing plasma shell, narrowband filters tuned to oxygen, hydrogen, or hydroxyl lines should light it up like a beacon. So why aren't they? The answer might lie in the wavelengths being observed. Most professional comet imaging focuses on the 365 nanometer OH line or the 427 nanometer CN line. These are standard cometary emissions produced by water and organic molecules breaking apart in sunlight. But if 3i Atlas is metal-rich, it might not emit strongly in those lines. Instead, it might emit in nickel, iron, and sodium lines, that professional pipelines are filtering out to reduce noise, the plasma boundary could be screaming in a colour NASA's instruments are deaf to. Or here's the alternative. Maybe the boundary isn't uniform. Maybe it's rotating. Maybe it's reacting to fluctuations in the solar wind, pulsing and shifting on timescales shorter than professional telescopes can capture with their long exposures. Amateurs taking hundreds of short exposures and stacking the best ones might accidentally capture the boundary at its brightest and sharpest, while professionals average it out into a blur. Either way, the implication is the same. The spindle shape might not be the object. It might be the ghost of the object, the electromagnetic shadow it casts as it tears through space. And if that's true, then the resolution war isn't about image quality. It's about what we're willing to call real. Is a plasma boundary real? Is a field structure real? Or does reality only begin at the solid surface and everything else is just glow? Because if we're being honest, we've never seen an interstellar object up close. Oumuamua passed too quickly for detailed observation. Borisov was studied from afar. 3I Atlas is the third confirmed visitor, and it's the first one amateurs can track with consumer equipment. We're making up the rules as we go. And the rules we're making depend entirely on which instruments we trust. Which brings us to the part of this story nobody wants to talk about. The oddities buried in official archives that suggest not everyone is being transparent. And transparency, once lost, is almost impossible to rebuild. Part 5. What NASA isn't showing. The archival oddities. There's a peculiar kind of silence that settles over a community when trust begins to crack. It's not loud, it's not dramatic, it's a slow withdrawal, a gradual realization that the information you're receiving might not be the information that exists. And in the astronomy forums dedicated to 3I Atlas, that silence started to spread in early December, when researchers began digging into the raw FITS files, archived by various observatories. FITS stands for Flexible Image Transport System. It's the standard file format for astronomical data, and it's supposed to contain everything, not just the image itself but the metadata. Observation timestamp, exposure duration, filter used, telescope orientation, temperature, air pressure. Every variable that might affect the data is recorded in the file header so future researchers can verify, replicate, and cross-check results. Metadata is the immune system of science. It's how we catch errors and confirm discoveries. But some of the FITS files released for 3I Atlas were missing fields, not all of them, not consistently. But enough to raise eyebrows. Observation angle entries listed as undefined, exposure chains incomplete. Some files lacked timestamps accurate to the second, listing only the date. For images of a fast-moving object where timing is critical, this is a red flag. Not proof of malfeasance, but proof of sloppiness at best. Now, let's be clear about the most likely explanation. Pipeline errors, automated systems scrubbing sensitive fields, data formatting inconsistencies between different telescopes and agencies, bureaucratic screw-ups that have nothing to do with hiding evidence and everything to do with institutional disorganization. Incompetence is almost always more plausible than conspiracy. But incompetence creates the space where conspiracy theories grow, because people assume that if something is missing, it was removed, not lost. And then there's the downscaling issue. Some of the released images appear to have been reduced in resolution before release, not blurred, downscaled. That's a different operation. Blurring leaves the original pixel count intact but smudges detail. Downscaling reduces the number of pixels, it's data compression, and when you compress an image, you destroy subpixel information permanently. Fine-edge structures, faint gradients, anything that exists between pixels gets averaged into oblivion. This is standard practice for public releases, especially for large data files that would otherwise crash servers or overwhelm casual users' bandwidth, but it's also a choice to prioritize accessibility over fidelity. And when that choice results in amateurs with full-resolution sensors seeing structures that professionals don't, the question becomes whether the choice was neutral or strategic. Were the images downscaled to make them manageable, or to make them safe? The debate here cuts to a deeper philosophical divide in how science communicates with the public. On one side are researchers who believe raw data should be public instantly, unprocessed and unfiltered. Let the community analyze it. Let independent eyes catch mistakes. Let transparency be the default. On the other side are institutions who argue that raw data is meaningless without context, that releasing uncalibrated images invites misinterpretation, that the public lacks the expertise to distinguish signal from noise, and so data should be curated first to avoid chaos. Both sides have valid points. Unprocessed data is noisy, confusing, and easy to misread, but curated data is editorialized. Someone decides what counts as signal and what counts as noise, and if the someone doing the deciding has institutional biases, career incentives to avoid controversy, or simply an outdated understanding of what the object might be, then curation becomes censorship by accident. This is not a new problem. Agencies have always delayed releases to avoid embarrassment. Mars face. Pulsars initially classified as LGM signals, little green men. The first exoplanet candidates dismissed as instrument noise. History is littered with examples of conservative institutions downplaying anomalies until overwhelming evidence forces acknowledgement. It's not malicious, it's structural. Large organizations move slowly, prioritize consensus, and avoid bold claims that might damage credibility. But the effect is the same whether the intent is caution or cover-up. When official images are soft, smooth, and structureless, and amateur images are sharp, detailed, and geometric, people assume something is being hidden. Maybe it is, maybe it's not. But the lack of transparency makes it impossible to tell the difference, and that impossibility is corrosive, because once you lose trust, every data point becomes suspect, every missing metadata field looks like redaction, every downscaled image looks like sanitization, and the community fractures into camps that no longer speak the same language. Some believe the institutions, some believe the amateurs, and some believe nobody, because when everyone has an incentive to shape the narrative, truth becomes just another story. So what is NASA not showing? Maybe nothing. Maybe the archival oddities are exactly what they appear to be at face value. Boring administrative failures, data management glitches, the mundane chaos of large organizations trying to standardize formats across decades of legacy systems. Or maybe the oddities are symptoms of a deeper reluctance to release data that contradicts expectations. A subtle, unconscious filtering where confusing images get delayed, problematic files get downscaled, and only the clean, interpretable data makes it to the public eye. Either way, the damage is done. Trust, once questioned, doesn't return easily, and the questions keep multiplying. Because if the archival data is incomplete, how do we verify anything? How do we know what we're not seeing? And if the answer is we don't, then what does that say about the structure of scientific knowledge in an age where citizen observers have tools that rival the professionals? Where does authority come from when the instruments disagree, and the data depends on who's holding the camera? These are the questions echoing through the forums as the calendar turns and Act 2 begins. Because the resolution war isn't about images anymore. It's about who gets to define reality when the tools we use to see start shaping what we're allowed to believe. And that's not a technological problem, that's a philosophical one, which means the next part of this story goes under the hood, into the mechanics of how these smart telescopes actually work, and whether they're revealing the truth or accidentally inventing it. Part 6. Smart Telescope AI. A blessing, a curse, or an accidental truth machine. There's a moment in the history of any technology where it stops being a tool and starts being a participant, where it doesn't just measure reality but interprets it. Smart telescopes crossed that line somewhere around 2022, and most people didn't notice. They were too busy being amazed by how easy it suddenly was to photograph galaxies from a suburban backyard with light pollution and no expertise. Point, click, let the algorithm do the rest. Magic. But magic is just sufficiently advanced technology you don't understand. And when you don't understand how something works, you can't tell the difference between revelation and hallucination. So let's pull back the curtain on what these devices are actually doing when they claim to show you the universe. Live stacking is the foundation. Traditional astrophotography required hours of manual exposure, precise tracking, and post-processing expertise. You'd take one long exposure, or several shorter ones, and combine them later on a computer using software like Deep Sky Stacker or PixInsight. It was time-consuming, error-prone, and required real skill. Smart telescopes automate that entire process in real time. The device takes dozens of short exposures, aligns them on the fly, and stacks them into a single composite image while you watch. It's like watching a Polaroid develop, except the Polaroid is assembling itself from 100 overlapping fragments. And here's where the AI enters. Modern smart telescopes use neural networks trained on thousands of astronomical images to identify and remove noise. They know what stars should look like. They know what galaxies should look like. They know what random sensor noise looks like, and they filter accordingly. But filtering is interpretation. The algorithm is deciding, pixel by pixel, what's signal and what's noise based on what it was taught to expect. And if the thing you're imaging doesn't match the training data, the algorithm has to guess. Now, this isn't unique to consumer telescopes. Professional observatories use similar techniques. DARPA's satellite reconstruction methods, developed for tracking objects in orbit, rely on sub-pixel feature detection across multiple frames. The process is called super resolution, and it's real science. If you take 100 images of something, each slightly offset, you can mathematically combine them to extract detail finer than any single image contains. It's not magic, it's signal processing, and it works. The amateur astrophotography community stumbled onto this years ago. Backyard observers using DSLR cameras discovered exoplanet transits by stacking thousands of frames and detecting brightness dips too small for any single exposure to capture. They beat the professionals not because their equipment was better, but because their workflow was different. More frames, shorter exposures, aggressive stacking, quantity over quality compounded into something remarkable. Smart telescopes are doing the same thing, but faster and smarter. And here's the hypothesis that's gaining traction among engineers who actually build these systems. They're not inventing structure, they're denoising faint plasma shapes. If 3i Atlas has a glowing boundary, but it's buried under atmospheric noise, sensor grain, and light pollution, a single exposure will show nothing. But stack 100 exposures, and the noise averages out while the signal builds. The plasma shell emerges not because the algorithm created it, but because it isolated it from the chaos around it. Think of it like listening to a whisper in a crowded room. One recording you hear nothing. 100 recordings, averaged together, and the whisper becomes audible because the random chatter cancels itself out while the consistent whisper reinforces. That's what stacking does. It turns faint, persistent signal into visible structure. But here's the uncomfortable flip side. What if the algorithm is too good? What if it's so aggressive at finding patterns that it starts detecting structures that are barely there, or fluctuating, or ambiguous? What if it's turning soft gradients into hard edges, fuzzy boundaries into geometric shapes, random brightness variations into repeating patterns? This is the curse hiding inside the blessing. Super resolution works, but it also amplifies bias. If the neural network was trained mostly on galaxies and star clusters, and you point it at a plasma-wrapped interstellar object, it might interpret the plasma as a solid surface. Not because it's lying, but because it's applying the wrong template. And this is why the debate has gone nuclear, because both sides can point to the same process and reach opposite conclusions. The engineers say the algorithm is stabilizing real features. The skeptics say the algorithm is imposing false structure, and both are right depending on what you assume about the underlying signal. If the plasma boundary is stable and geometric, the algorithm is revealing it. If the plasma boundary is chaotic and amorphous, the algorithm is sculpting it into something it's not. There's another layer to this: ring artifacts, ghost edges, stacking bias. These are real problems in automated image processing. When you align hundreds of slightly different frames, small errors in alignment can create false rings around bright objects. Over-sharpening can introduce halos. Poor flat field correction can leave gradients that look like structure. Experienced astrophotographers know how to identify and eliminate these artifacts. But consumer-grade smart telescopes designed for ease of use sometimes bake the artifacts into the final image without the user ever knowing they're there. So how do we know if the spindle is real? The answer is frustratingly unsatisfying. We look for consistency. If the artifact appears in some images but not others, it's probably an artifact. If it appears in all images, across different equipment, different locations, different processing methods, it's probably real. And by that, standard, the spindle passes the test. But passing the test doesn't tell us what it is. It just tells us something is there. And that's where we're stuck. Trapped between tools that might be too good at finding patterns and tools that might be too conservative to see them. Between algorithms that reveal and algorithms that invent. between signal and noise with no neutral ground to stand on, because the truth is, every instrument shapes what it sees. Professional telescopes filter wavelengths, smart telescopes enhance edges, human eyes prioritize contrast. There is no unmediated view of reality. There's only layers of interpretation, and the question of which layer you trust. But maybe trust isn't the right question. Maybe the question is whether the interpretation is consistent with physics. And that brings us to the next piece of the puzzle, the spectral blindness factor. The possibility that NASA's instruments aren't wrong, they're just deaf to the frequencies where 3i Atlas is shouting loudest. Part 7. The spectral blindness factor. Light is not a single thing, it's a spectrum. A rainbow of wavelengths ranging from radio waves kilometers long to gamma rays smaller than atoms. Our eyes see only a thin slice of that spectrum, the part we call visible light, spanning roughly 380 to 740 nanometers. But the universe doesn't care what we can see. It radiates across the entire electromagnetic spectrum, and if you want to understand what's really out there, you need instruments that can capture what your eyes cannot. This is why astronomical imaging is never neutral. Every camera, every telescope, every sensor is designed to be sensitive to specific wavelengths and blind to others. You make choices. You use filters. You optimize for the science question you're trying to answer. And those choices determine what you see. They also determine what you miss. Professional telescopes studying comets typically use narrowband filters tuned to emission lines associated with common cometary molecules. The hydroxyl line at 365 nanometers, the cyanogen line at 427 nanometers. These are the fingerprints of water and organic compounds breaking apart under solar radiation. If you're looking for a normal comet, these filters give you the cleanest, most interpretable data. But if you're looking at something abnormal, something that doesn't emit in those lines, your carefully chosen filters become blinders. And here's the critical point. Professional instruments often block the brightest emission lines to protect sensitive detectors. Sodium, for example. The sodium doublet at 589.0 and 589.6 nanometers is one of the most intense emission lines in the sky when ionized sodium is present. It's so bright it can saturate sensors and wash out fainter signals. So observatories use sodium rejection filters, not to hide anything, just to see other things more clearly. But if the object you're studying happens to be emitting primarily in sodium wavelengths, and you've blocked sodium, then you've just made yourself blind to the object's defining characteristic. It's like trying to study a neon sign through a filter that blocks neon. You'll see the glass tube maybe, but you won't see the glow. And the glow is the whole point. This is the theory gaining traction to explain why NASA's images look so different from amateur captures. The agency's instruments are optimized for dust physics and standard cometry emissions. They're designed to study objects like Halley's Comet, Hale-Bopp, Neowise, objects that fit the model, but 3i Atlas might not fit the model. If it's metal-rich, emitting strongly in nickel, iron and sodium lines, then narrowband filters tuned for organics will see almost nothing. Meanwhile, consumer-grade RGB sensors with broad spectral response will capture the full glow. There's precedent for this. Oumuamua's colour measurements were inconsistent across different observatories using different filters. Some saw it as red, some saw it as grey. The discrepancy was eventually attributed to differences in how each instrument weighted different wavelengths. Hale-Bopp, back in 1997, had a faint sodium tail that was almost missed because most observations focused on the bright dust tail. The sodium emission was there, but you had to look in the right wavelength to see it. Spectral filtering doesn't just affect brightness, it affects structure. A plasma boundary emitting in narrow wavelengths might appear as a sharp-edged shell in broad-spectrum imaging, but be invisible in narrow-band imaging. Conversely, a dust cloud scattering sunlight might show up clearly in professional filters, but appear faint and diffuse in consumer cameras. The same object can have multiple appearances depending on which colours you're allowing through the lens. And this brings us to an uncomfortable realization. There's no such thing as the true image. There's only the image as seen through this filter, or this sensor, or that algorithm. Every photograph is a choice about what to emphasize and what to ignore. Professional observatories choose to emphasize scientifically relevant wavelengths. Amateurs choose to emphasize visual drama. Neither is wrong, but neither is complete. So when we ask why 3i Atlas looks different in every image, part of the answer is simple. It looks different because we're looking at different colours. Professionals are seeing it in the ultraviolet and near-infrared, focused on dust. Amateurs are seeing it in the visible spectrum, capturing gas emissions. And both are real. Both are partial, both are incomplete without the other. But there's a deeper issue here. If the object is electrically charged, and if it's interacting with the solar wind in unusual ways, it might emit most strongly in wavelengths that nobody is prioritizing. There are emission lines associated with ionized metals that aren't part of standard observing programs. Nickel at 352 nanometers, iron at 372 nanometers, chromium at 426 nanometers. If 3i Atlas is shedding these metals, and they're glowing under solar wind bombardment, then both professional and amateur instruments might be missing the brightest part of the show. And that's where speculation starts to blend with physics. If the object is electrically charged, if it's developing a plasma sheath, if it's emitting in wavelengths we're not measuring, then the resolution war isn't about image quality, it's about incomplete data. We're all blind in different ways, and the thing we're looking at is exploiting the gaps in our vision. Which brings us to the next question. What exactly is a plasma sheath? Why would 3i Atlas have one? And could it explain the geometric shapes that keep appearing in amateur images? Part 8. Plasma sheaths, Langmuir boundaries, and the energy shell hypothesis. Plasma is the fourth state of matter: solid, liquid, gas, plasma. Most people forget that last one because we don't encounter it in daily life, except when we do and we call it something else. Lightning, neon signs, the sun. Plasma is what happens when you heat gas so much that electrons rip free from atoms, leaving a soup of charged particles that behaves more like a fluid with memory than a simple gas. It conducts electricity, it responds to magnetic fields, it forms structures, and when an object moves through plasma, the object doesn't just pass through, it disturbs the plasma, it creates boundaries, shock waves, wakes. These aren't metaphorical, they're physical structures governed by electromagnetic forces, and they can be as sharp and defined as a solid surface, even though they're made of nothing but charged particles and fields. A Langmuir sheath is one such boundary. It's the region around an object in plasma where the electric potential changes sharply. Think of it as the border between the object's local electric field and the surrounding environment. Spacecraft in orbit develop Langmuir sheaths. Satellites develop them. Any charged object moving through ionized gas develops them, and they can look to a distant observer using the right instrument, like solid shells. Now apply that to 3i Atlas. If the object is shedding ionized gas, particularly metal ions like sodium, nickel, or iron, it will be surrounded by a cloud of charged particles. As the solar wind, itself a plasma, flows past the object, it will interact with that cloud. The interaction creates a boundary, a bow shock, a magnetopause, a plasma sheath, and that sheath could be significantly larger than the solid nucleus inside it. Imagine a car driving through fog. You can't see the car directly, but you can see the shape of the fog disturbed by the car's passage. The fog wraps around the car, creating a visible outline. That outline is not the car, but it accurately traces the car's shape. Now replace the car with a comet nucleus, and replace the fog with ionized gas, and you get the basic idea. The plasma sheath is the outline, and what amateur telescopes might be imaging is not the object itself, but the electromagnetic disturbance it creates as it moves. This would explain the hard edges. Plasma boundaries can be sharp because they're regions of rapid change. Inside the boundary, the electric field is dominated by the object. Outside, it's dominated by the solar wind. The transition between those two regimes can happen over distances of just a few meters, and to a telescope light hours away, a few meters looks like a razor line. It would also explain the geometry. Plasma sheaths are shaped by the flow of the surrounding medium. If the solar wind is flowing uniformly, the sheath becomes elongated in the direction of flow like a teardrop. If the object is rotating, the sheath might wobble or pulse. If the object's emission is uneven, the sheath could be asymmetric. But if the emission is steady and the solar wind is calm, the sheath could be remarkably symmetric and stable, which matches what observers are seeing. And here's the kicker. Stacking algorithms are really good at finding edges, even faint ones. If there's a soft gradient in brightness across the plasma boundary, stacking will amplify it into a sharp line. This isn't the algorithm making things up. It's the algorithm doing exactly what it's supposed to do, revealing faint structure by averaging out noise. The structure is real. It's just not solid. It's a field boundary rendered visible. But professional narrowband filters might not see this at all. If the plasma is emitting primarily in sodium and metal lines, and those lines are blocked, the sheath becomes invisible. The nucleus might still be faintly visible as a point source or small blob, but the surrounding structure disappears, which is exactly what NASA's images show. Not because the structure isn't there, but because the instrument isn't sensitive to the wavelengths where the structure glows. There's a historical parallel here. Ion probe missions to comets have detected plasma boundaries that appeared as hard-edged structures in particle detectors. The Giotto mission to Halley's Comet in 1986 measured a bow shock that looked, in the data, like a geometric shell. But it wasn't a physical shell. It was a pressure boundary where the solar wind piled up against the comet's outgassing. From a distance, using optical instruments, that boundary might have been invisible. But to a probe passing through it, it was unmistakable. So the hypothesis forming here is that 3I Atlas might be unusually charged, perhaps because it's interstellar, perhaps because its composition includes conductive materials, perhaps because it's interacting with the solar wind in ways typical solar system comets do not. And that charge is creating a plasma sheath large enough to be detected by consumer-grade telescopes using the right wavelengths and the right processing. If that's true, then the spindle shape isn't the comet. It's the comet's ghost, its electric shadow, its boundary layer rendered visible by accidental super-resolution, performed by smart telescope algorithms trained to find edges, and the professionals aren't seeing it not because they're hiding it, but because they're not looking in the right colour. But there's a speculative edge to this that needs to be acknowledged. Could the plasma boundary be masking a solid core? Could there be something inside the sheath that's completely hidden? It's possible, but unlikely. Plasma sheaths don't block light. They emit it. If there's a solid nucleus, it should still be visible as a point source, just dimmer and surrounded by glow. The fact that amateurs see structure but no distinct nucleus suggests either the nucleus is very small, very dark, or fragmenting. All of which are plausible for an interstellar object that's been travelling through the void for who knows how long. And this is where the science blends into speculation. Because once you accept that the shape might be plasma, you open the door to asking whether the plasma is behaving normally, whether the glow is passive or active, whether there's something about this object's composition, rotation, or electrical state that's creating phenomena we don't have models for. And speculation, when unchecked, becomes conspiracy, which is exactly what happened next. Because by late December, the forums had moved from debating optics and plasma physics to debating whether NASA was deliberately sanitizing images to hide something they didn't understand. And that's where things got messy. Part 9. The conspiracy web around image releases. There's a gravity to distrust. Once it starts, it pulls everything into its orbit. Small discrepancies become evidence, mundane delays become suspicious, and the absence of information becomes proof that information exists and is being withheld. By mid-December 2024, the astronomy forums weren't just debating image processing techniques. They were debating intent, motive, cover-up. The resolution war had become a conspiracy web, and the web was growing. Let's lay out the leading claims circulating in these spaces. First, that NASA sanitizes images using Gaussian blur masks before public release to hide fine structure. Second, that agencies downsample raw data to destroy sub-pixel information that might reveal anomalies. Third, that raw data is intentionally delayed to allow time for edits, corrections, or redactions before anyone outside the institution can analyze it. These aren't fringe theories whispered in dark corners. They're mainstream suspicions repeated openly in communities of educated, technically literate observers who feel gaslit by institutional opacity. And here's the frustrating part. Some of these claims are partially true, not the conspiracy versions but the underlying practices. Agencies do apply Gaussian smoothing to reduce noise. They do downsample large files to make them accessible. They do delay raw data releases for quality control. These are standard pipeline steps documented in technical manuals, performed for legitimate reasons. But standard doesn't mean neutral. Every choice about how to process data is a choice about what to show and what to hide. And when those choices consistently result in amateurs seeing structure that professionals don't, the legitimacy of those choices gets questioned. Consider the psychology here. Scientists, especially at large institutions, are conservative by training and necessity. Publishing a bold claim that turns out to be wrong can end careers, so there's immense pressure to avoid releasing data that might be misinterpreted or that contradicts expectations. If an image shows something confusing, the instinct is to clean it up, process it more carefully, and only release it when you're confident you understand what it shows. This isn't conspiracy, it's professionalism. But the effect is that confusing, ambiguous, or anomalous images get delayed or sanitized, while clean, interpretable images get fast-tracked. And that creates a selection bias in what the public sees. The images that make it through the pipeline are the ones that fit existing models. The ones that don't fit get held back, not out of malice, but out of caution. And so the public narrative becomes skewed toward the predictable, the explainable, the safe. Meanwhile, amateurs with no reputations to protect and no institutional oversight release everything. The good, the bad, the confusing, the anomalous. And sometimes the confusing anomalies are the most interesting things in the data. There's a push within parts of the scientific community for real-time, unfiltered data streams. The argument is simple. Transparency builds trust. If raw data is public instantly, anyone can analyze it, and the community can collectively decide what's signal and what's noise. No single institution controls the narrative. No pipeline introduces bias. The data is what the data is, and interpretation becomes a collaborative process rather than a top-down pronouncement. But there's a counter-argument. Raw data is raw. It's uncalibrated, unprocessed, full of artifacts, instrument noise, and systemic errors that only experts know how to remove. Releasing it without context invites misinterpretation. People will see patterns that aren't there. They'll make claims that aren't supported. They'll generate panic or confusion based on misunderstandings. And the institution then has to spend time and resources debunking false claims instead of doing science. Both sides have merit, and the tension between them is what's fueling the conspiracy web. Because when institutions withhold data, even for good reasons, they create information asymmetry. And information asymmetry breeds suspicion. Why is this image delayed? What are they checking? What don't they want us to see? The questions multiply faster than the answers, and eventually the gap between question and answer fills with speculation. And here's where it gets darker. Some anomalies genuinely do only appear in early amateur data, and never in official releases. The sodium spikes, the spindle structure, the repeating geometry. These features were documented by amateurs in late November, but never appeared in any official NASA image release. Why? Maybe because professional instruments weren't sensitive to them. Maybe because the processing pipeline smoothed them out. Maybe because they were classified as artifacts and discarded. Or maybe because someone at some level of the decision chain looked at the data, didn't understand it, and decided it was safer not to publish it than to publish something controversial. We don't know. And that's the problem. The lack of transparency makes it impossible to distinguish caution from censorship. And in the absence of transparency, people assume the worst. They assume agencies are flattening information to prevent public misinterpretation or panic. They assume the truth is being managed rather than reported. And whether or not that's true, the perception corrodes trust in ways that are hard to repair. This isn't unique to 3i Atlas. It's a pattern that repeats across every field where institutions control access to information. Climate data, pandemic statistics, economic indicators, UFO reports. Whenever there's a gap between what the public can see and what the institutions see, conspiracy theories rush in to fill the void. Not because people are irrational, but because information asymmetry is inherently suspicious. And the irony is that institutions often create their own problems by trying to avoid them. By withholding confusing data to prevent panic, they create the impression that something is being hidden, which generates more panic than the data itself would have. By processing images to make them cleaner and more interpretable, they erase details that amateurs detect, which makes it look like a cover-up. By delaying releases for quality control, they give conspiracy theories time to incubate and spread before the facts can catch up. So where does that leave us? Stuck in a hall of mirrors where every reflection is distorted and nobody can agree on what's real. The professionals say the amateurs are seeing artifacts. The amateurs say the professionals are sanitizing truth. The conspiracy theorists say everyone is lying, and the data, the actual photons captured by actual sensors, sits in the middle, interpreted a dozen different ways depending on who's looking and what they want to see. But here's the thing. This isn't the first time instruments have misled us. It's not the first time experts disagreed over ambiguous data. And it's not the first time the public lost faith in institutional explanations. History is full of cases where instruments fooled everyone, where scientists spent years arguing over artifacts, where reality turned out to be stranger than the consensus allowed. And understanding those cases might help us understand what's happening now, or at least help us avoid jumping to conclusions before we know what we're looking at. Part 10. Past cases where instrument bias misled the world. In 1983, the infrared astronomical satellite IRAS detected a mysterious object in deep space that didn't match any known category. It was too bright to be a distant galaxy, too cold to be a star, and located in a region of sky where nothing should exist. The media went wild. Headlines screamed about the possible discovery of Planet X, a hidden world lurking at the edge of the solar system. Speculation ranged from brown dwarfs to rogue planets, to inevitably alien megastructures. The truth was far more mundane and far more embarrassing. The object was an instrumental artifact, a ghost image created by scattered infrared light within the telescope's optical system. There was no planet. There was no mystery object. There was only a design flaw that nobody caught until after the discovery was announced. The retraction was quiet. The damage to public trust was loud. Or consider the case of ALH 84001, the Martian meteorite. In 1996, NASA scientists announced they had found evidence of fossilized microbial life in a rock that had been blasted off Mars and landed in Antarctica. The structures inside the rock looked like bacteria. The chemical signatures looked like biological activity. It was, potentially, the most important discovery in human history. Proof that life had existed beyond Earth, except it wasn't. Other researchers soon demonstrated that every single feature in the rock could be explained by non-biological processes. The tiny structures weren't fossils, they were mineral formations. The chemical signatures weren't from life, they were from contamination or ordinary geological reactions. The shapes that looked like bacteria were just shapes. The human brain's tendency to see life where none exists had led scientists momentarily astray. The lesson from ALH 84001 isn't that the scientist was stupid. It's that ambiguous data can support multiple interpretations, and the interpretation you favour depends on what you're expecting to find. If you're looking for life, you'll see life. If you're looking for geology, you'll see geology. And sometimes it takes years of argument before the community converges on an answer. Then there's the Venus phosphine debacle. In 2020, researchers announced the detection of phosphine gas in Venus's atmosphere, a potential biosignature since phosphine on Earth is mostly produced by biological processes. The discovery was based on spectroscopic data from ground-based telescopes. The signal was weak but seemed real. The implications were staggering. Maybe Venus, despite being a hellish wasteland of sulfuric acid and heat, harboured life in its high-altitude clouds. But the signal was a processing artifact. Other teams analysing the same data found that the spectral line attributed to phosphine was actually sulfur dioxide being misidentified due to pipeline overprocessing. The algorithm used to remove noise had introduced a ghost signal. The phosphine wasn't there. The discovery evaporated. And once again, the public was left wondering whether to trust anything scientists announce if the tools themselves can't be trusted. These stories aren't anomalies, they're warnings. Instruments don't just detect reality, they interpret it. And sometimes they interpret it wrong. Sometimes a sensor glitch creates a signal that looks real. Sometimes an algorithm enhances noise into structure. Sometimes an observer sees what they expect to see, because the data is ambiguous enough to support any narrative. And when experts disagree, which they often do, the disagreement can last for years or decades before consensus forms. The point here isn't that science is broken, it's that science is a process, not a pronouncement. Data is messy. Instruments have biases. Models have limits. And when you're looking at something genuinely new, something that doesn't fit existing categories, the tools you have might not be adequate to tell you what you're seeing. You might see ghosts, you might see artifacts, or you might see something real that everyone else thinks is a ghost because it's too strange to be believed. And that brings us back to 3i Atlas, the conflicting data, the amateur structures, the professional blobs, the sodium spikes, the plasma boundaries. Are we looking at another IRAS ghost, another ALH false positive, another Venus phosphine artifact, or are we looking at something genuinely anomalous that doesn't fit our models and won't fit our models until we build new ones? The honest answer is we don't know yet, and that uncertainty is uncomfortable. It's easier to declare victory for one side or the other, to say the amateurs are wrong, or the professionals are hiding something. But history suggests a third option, that both sides are partially right and partially wrong, and the full picture won't emerge until we stop arguing about who's correct and start asking what the instruments are actually telling us when we combine all the data, instead of cherry-picking the parts that fit our preferred narrative. Because the universe doesn't care about our preferences. It doesn't care about our models. It doesn't care whether we're ready to understand it. It simply is, and sometimes it shows us things we're not equipped to see clearly, which is why the next part of this story moves beyond the Resolution War and into the wider context of discoveries made this year that reframe everything: breakthroughs in AI deconvolution, exomoon announcements, phantom structures in deep space tracking, solar wind surges, and new physics that reminds us how little we actually know. These aren't distractions from the story of 3i Atlas. They're the story, because the real question isn't what this one object is, it's what happens when our tools evolve faster than our understanding, and we're forced to confront the possibility that reality is more layered, more ambiguous, and more strange than any single instrument can reveal. Part 11. The new AI deconvolution model that rewrites everything, 2025. Artificial intelligence is eating the world. That's the phrase that gets thrown around in tech circles, and it's annoyingly true. AI is rewriting how we communicate, how we create, how we diagnose disease, how we wage war. And now, in 2025, it's rewriting how we see the universe, literally. Because this year, a team of researchers published a new AI-driven deconvolution model that does something nobody thought possible. It reconstructs sub-pixel structure from noisy astronomical images with near-perfect stability. And if that doesn't sound revolutionary, you're not paying attention. Deconvolution, as we've discussed, is the process of reversing blur. Light travelling through a telescope gets smeared by atmospheric turbulence, optical imperfections, and sensor limitations. Deconvolution tries to undo that smearing mathematically, to recover the sharp image that existed before the blur. Traditional deconvolution works, but it's fragile. Push it too hard and you introduce artifacts, rings, halos, ghost edges. The signal gets contaminated by the cure. But AI deconvolution is different. Instead of using fixed mathematical formulas, it learns. It's trained on thousands of blurred and sharp image pairs until it internalizes the patterns of how blur happens. Then, when you feed it a new blurred image, it doesn't just apply a formula. It guesses what the original sharp image probably looked like based on everything it's learned. And the guesses, astonishingly, are almost always right. The model published this year takes that concept to the next level. It doesn't just sharpen, it super resolves. It extracts detail finer than the resolution limit of the original sensor by analyzing correlations across multiple frames. If you take 10 images of the same object, each with slightly different noise and slightly different atmospheric distortion, the AI can combine them to produce an image sharper than any single frame could ever be. It's not magic, it's statistics weaponized by neural networks that have seen more astronomical images than any human astronomer could in a lifetime. And here's where it connects to 3i Atlas. The smart telescopes amateurs are using, they're running early versions of this kind of technology. The stacking algorithms that revealed the spindle shape are cousins to the super-resolution AI. They're not as sophisticated yet, but they're moving in that direction. And if the trend continues, within a few years, consumer-grade equipment will have resolution capabilities that rival or exceed professional observatories, not because the optics are better, but because the processing is smarter. Think about the implications. If an amateur with a $1,000 telescope and open-source AI software can outresolve $1 million observatory, what does that do to the hierarchy of astronomy? What happens when the best images of an object come not from NASA but from a hobbyist in Nebraska? What happens when citizen observers collectively generate higher fidelity data than any single institution can produce? It's already happening. Exoplanet discoveries, supernova detection, asteroid tracking. Amateurs are making contributions that were unthinkable a decade ago. And the tools are only getting better. The AI deconvolution model published this year is open source. Anyone can download it. Anyone can run it. Anyone with a decent computer and a backyard telescope can now produce images that look like they came from Hubble. But there's a darker side. If truth becomes algorithm dependent, whose algorithm do we trust? The AI model works by learning from training data. But what if the training data is biased? What if it was trained mostly on galaxies and nebulae, and now you're using it on an interstellar comet? It might impose structure that looks plausible but isn't real. It might smooth away features that don't match its training. It might, in other words, lie to you without knowing it's lying. This is the paradox of AI-assisted astronomy. The tools are powerful enough to reveal things we couldn't see before, but they're also powerful enough to create things that aren't there. And telling the difference requires understanding not just the object being imaged, but the algorithm doing the imaging. How was it trained? What biases does it carry? What assumptions is it making about the nature of the data? These questions don't have easy answers, and as the technology spreads, as more observers adopt these tools, the resolution war is going to intensify. Because every new AI model will see the universe slightly differently. Every algorithm will make different trade-offs between sharpness and accuracy, and every image will be, in some sense, an interpretation rather than a measurement. We're moving toward a future where the line between observation and synthesis blurs, where the data and the model become inseparable, and where the question, what did you see, gets replaced by what did the algorithm think you saw? And 3i Atlas is just the beginning, the first object caught in the crossfire of human observation and machine vision, the first controversy where the shape of reality depends on whose software you're running. But it won't be the last, because the universe is full of strange objects, and our tools are getting strange too. And when strange tools look at strange objects, the results are unpredictable. Sometimes you get clarity, sometimes you get confusion, and sometimes you get something in between that nobody knows how to interpret, which is exactly what happened this year with another discovery that shook the astronomy world and made everyone question their instruments all over again. Part 12, the 25 exomoon shock announcement. May 2025. A team of researchers announced they had detected the second confirmed exomoon, a moon orbiting a planet orbiting a distant star. The first exomoon candidate, discovered back in 2017, had been controversial and never fully accepted. Too much uncertainty, too much noise, but this one seemed solid. Multiple detection methods, consistent data, a clear signal, until people started looking closer. The exomoon's reflectance spectrum was wrong. Not slightly off, deeply, fundamentally wrong. It was reflecting light in wavelengths that didn't match any known material. Too bright in the near-infrared, too dark in the visible. Spectral features that suggested both ice and rock, and something else that didn't fit any model. Observers using different instruments reported wildly different characteristics. One team saw a bright, icy surface. Another saw a dark, carbon-rich surface. A third saw variability, as if the surface was changing over time or rotating to reveal different materials, and the controversy exploded. Was this a real exomoon with an exotic composition, or was it an instrumental artifact created by the challenge of imaging a tiny faint object next to a massive bright planet? Were the spectral anomalies real, or were they cross-contamination from the planet's light bleeding into the moon's signal? Were different instruments seeing different realities, or were they all seeing noise and interpreting it differently? The debate is still ongoing. No consensus has formed. But the exomoon case is a perfect parallel to 3i Atlas. Same pattern. Different tools produce different results. Professionals disagree. Amateurs contribute data that complicates rather than clarifies. And the object itself remains ambiguous, refusing to fit neatly into existing categories. The lesson here is that new types of objects often look wrong. They look wrong because our instruments are optimized for known types. A spectrograph designed to study gas giants will struggle with an exomoon. A comet imaging pipeline designed for icy bodies will struggle with a metal-rich interstellar visitor. The tools shape what we see, and when the tools aren't designed for the thing we're looking at, the data becomes unreliable. This is why spectral mismatches matter. If different instruments are sensitive to different wavelengths, they'll produce different portraits of the same object. And if the object's composition is unusual, the disagreements will be extreme. The exomoon might be icy in the infrared and rocky in the visible, because it has a layered structure, or because it's outgassing selectively, or because our models of how surfaces reflect light are incomplete. Similarly, 3i Atlas might appear as a blob in narrowband filters and a spindle in broadband sensors, not because one is wrong, but because each is capturing a different aspect of a complex multi-component system. The nucleus, the plasma sheath, the interaction zone with the solar wind. These are separate structures with separate emission mechanisms, and depending on which structure your instrument is sensitive to, you'll see a different object. The broader point is this. When you discover something genuinely new, something that doesn't fit your expectations, the first response is always skepticism. It must be an artifact. It must be an error. It must be noise. Because accepting that it's real means accepting that your models are incomplete. And models, once established, are hard to change. They have inertia. Careers are built on them. Textbooks are written around them. Admitting they're wrong is admitting you don't understand the thing you've spent your life studying. But sometimes the models really are wrong. Sometimes the universe hands you an object that doesn't fit, and instead of forcing it into a box it doesn't belong in, you have to build a new box. Or admit that boxes might not be the right metaphor at all. And that's uncomfortable. It's destabilizing. It's the kind of thing that makes scientists defensive, institutions cautious, and the public suspicious. So the exomoon shock announcement isn't just about an exomoon. It's about the growing realization that our instruments are hitting their limits, that the universe is more diverse, more complex and more strange than the categories we've carved it into. That the next generation of discoveries might not be things we recognize. They might be things we don't even have words for yet. And 3i Atlas might be one of them, but it's not alone. Because this year brought another case of instruments seeing things nobody can explain. And this time, it wasn't amateurs. It was a national space agency confronting the exact same problem the amateurs have been shouting about. Part 13. China's ghost image problem in deep space tracking. In August 2025, Chinese aerospace researchers published a technical report that most people outside the field ignored. It detailed a recurring problem in their Tianwen deep space tracking system. During high-velocity near-Earth object passes, the tracking algorithms were generating phantom structures, false edges, repeating geometric patterns that appeared in processed images but didn't correspond to any physical features on the objects being tracked. The problem was traced to algorithmic overcorrection. The tracking system, designed to stabilize fast-moving targets and remove motion blur, was applying edge enhancements so aggressively that it was inventing structure. Small brightness gradients, random noise spikes, and sensor artifacts were being interpreted as real edges and amplified into visible features. The objects looked more defined, more geometric, more solid than they actually were, and for months nobody caught it. This is a national grade system, built by experts, used for critical tracking of objects that could pose impact risks to Earth. And it was producing ghost images, not because the engineers were incompetent, but because the algorithms were doing exactly what they were told to do. Find edges, enhance them, make the target visible. The fact that some of those edges were hallucinations didn't stop the algorithm from rendering them as confidently as it rendered the real ones. And here's the parallel. If China's tracking system can create false edges through overcorrection, why can't amateur smart telescopes? If a national agency with unlimited resources can produce phantom structures, why are we so certain that the spindle seen in backyard images is real? The answer is we're not certain. We can't be certain. Because the same process that reveals faint structure also risks creating false structure. The line between clarification and fabrication is thinner than anyone wants to admit. But there's a counter-argument here too. The Chinese report documented the problem because they caught it. They ran tests. They imaged objects with known shapes and saw that the algorithm was adding detail that shouldn't be there. They identified the bug and fixed it. And crucially, the phantom structures were inconsistent. Different observations of the same object produced different ghost features. That's how you know it's an artifact. Artifacts don't replicate. With 3i Atlas, the structure replicates. The spindle appears again and again across different observers, different equipment, different processing methods. That consistency suggests the structure is real, or at least that it's being generated by a consistent signal that all the algorithms are responding to in the same way. Which doesn't prove it's physical, but it does suggest it's not random noise. The deeper lesson from China's ghost image problem is that even sophisticated systems make mistakes. Trusting instruments isn't naive, but trusting them blindly is dangerous. Every observation needs verification. Every algorithm needs testing. Every surprising result needs skepticism. And when multiple independent systems produce the same surprising result, that's when you start to believe. Not before. And this is where we are with 3i Atlas. Multiple systems, same result. But no verification from the systems we're supposed to trust most. Professional observatories aren't seeing the structure, or they're not reporting it, or they're dismissing it as artifact without investigating further, and that dismissal, whether justified or not, is feeding the conspiracy theories. Because if even China's national tracking system can suffer from ghost images, why should we believe NASA's images are clean? The answer is, we shouldn't believe automatically. We should demand transparency. We should demand raw data. We should demand that institutions explain not just what they see, but how they process what they see and what assumptions are baked into that processing. Because in an age where algorithms mediate every observation, the algorithm is part of the observation. You can't separate the two, and if you're not willing to open the algorithm to scrutiny, you're asking for blind trust. And trust, as this entire story demonstrates, is not freely given anymore. But algorithms aren't the only variable affecting what we see. The environment matters too. The conditions in space, the solar wind, the magnetic fields, the plasma itself. And this year, there was an event that might have changed everything about how 3i Atlas appeared to observers, a surge in the solar wind that nobody predicted, and that might explain why the object looked so different at different times. Part 14, the solar wind spike of August 2025. The sun is not constant. It breathes, it pulses, it hurls radiation and charged particles into space in waves that wash over the solar system like tides. Most of the time, the solar wind is predictable, a steady stream of protons and electrons flowing outward at around 400 kilometers per second. But sometimes the sun hiccups, flares erupt, coronal mass ejections explode outward, and the solar wind spikes to 3 or 4 times its normal speed, carrying magnetic chaos with it. August 2025 saw one of those spikes. The European Space Agency's solar orbiter detected a sudden surge in solar wind velocity, accompanied by a sharp increase in magnetic field strength. The event lasted about 72 hours. During that window, any object moving through the inner solar system would have experienced dramatically different plasma conditions: higher particle density, stronger magnetic pressure, more intense bombardment of charged particles. The spike wasn't just a minor fluctuation. Solar wind velocity jumped from its typical 400 km per second to nearly 1500 km per second in some regions. The interplanetary magnetic field, normally around 5 nanotesla at Earth's orbit, surged to nearly 30 nanotesla. These are the kinds of conditions that trigger geomagnetic storms on Earth, that create auroras visible at mid-latitudes, that can disrupt satellite communications and power grids. They're violent, chaotic, and relatively rare. And they transform the plasma environment of the inner solar system completely. During normal conditions, the solar wind flows outward from the sun in relatively smooth streams. High-speed streams from coronal holes mix with slower streams from the sun's equatorial regions, creating interaction zones where the plasma compresses and heats. But during a coronal mass ejection or a major solar flare, all that organization breaks down. A bubble of magnetized plasma erupts from the sun, carrying billions of tons of material at speeds that dwarf the normal flow. It plows through the ambient solar wind like a shockwave, compressing everything in its path. And this matters for 3i Atlas, because plasma boundaries are not static. They respond to the solar wind. When the wind is calm, the boundary around an outgassing comet or ionized object is relatively stable. But when the wind surges, the boundary compresses, it brightens, it shifts shape. Spacecraft have measured this effect directly. The magnetospheres of planets shrink and expand based on solar wind conditions. There's no reason to think a plasma sheath around a comet would behave differently. Earth's magnetosphere provides the clearest example. During quiet solar wind conditions, the magnetopause, the boundary between Earth's magnetic field and interplanetary space, sits about 10 Earth radii upstream from the planet. But during a strong solar wind surge, that boundary can compress to just 6 or 7 Earth radii. The entire magnetic envelope shrinks under pressure. And on the downstream side, the magnetotail, normally a relatively organized structure, becomes turbulent and chaotic. Magnetic reconnection events multiply, plasma flows accelerate, the whole system responds dynamically to the changing external conditions. Now, scale that down to a comet-sized object. 3I Atlas doesn't have a global magnetic field like Earth, but if it's outgassing ionized material, particularly metal ions like sodium or nickel, it will have a local plasma environment, an induced magnetosphere, a region where the solar wind interacts with the object's own emission, and that region will expand and contract, brighten and dim based on solar wind pressure. So if 3I Atlas was being imaged during or shortly after the August surge, its plasma boundary might have been unusually bright and geometrically distorted. The spindle shape that amateurs saw could have been an exaggerated version of a boundary that, under calm conditions, would be much fainter and less defined, which would explain why earlier images taken before the surge showed less structure, and why later images, after the wind calmed, might show the structure fading. The physics here is well understood. When solar wind pressure increases, it compresses the plasma around the object. That compression heats the plasma, increasing its emission. Ions that were diffuse become concentrated. Boundaries that were fuzzy become sharp. And structures that were invisible in normal conditions suddenly light up like they've been spotlit. It's the same reason auroras intensify during geomagnetic storms. More energy input, more emission, more visible structure. But there's another effect too. The enhanced solar wind carries stronger magnetic fields, and those fields can interact with any magnetic structures in or around the comet. If 3I Atlas has conducting material, even a small amount, the changing magnetic field will induce electrical currents. Those currents create their own magnetic fields, which push back against the solar wind, creating pressure boundaries and possibly even bow shocks. These electromagnetic structures can have sharp gradients and well-defined geometries. They're not solid, but they behave like barriers, and in imaging data they can appear as distinct edges. This is testable, or it should be. By correlating the dates of amateur observations with solar wind data from Solar Orbiter and other monitoring spacecraft, you could check whether the clearest spindle images coincide with periods of elevated solar wind activity. If they do, that supports the plasma boundary hypothesis. If they don't, the correlation fails and you're back to square one. The Solar Orbiter data is publicly available, so is data from NASA's Parker Solar Probe, from the Advanced Composition Explorer at the L1 Lagrange point, from ground-based magnetometers and ionospheric monitors. The tools exist to do this analysis. You could plot solar wind velocity, density, and magnetic field strength as a function of time through November and December 2024. Then overlay the timestamps of amateur observations. Look for correlations. See if the most geometric, most structured images cluster around periods of disturbed solar wind. But here's the problem. Most amateur observers don't timestamp their data with the precision needed for this kind of analysis. They know the night they observed, but not the exact hour or minute, and solar wind conditions fluctuate on timescales of hours. Without precise timing, the correlation is impossible to verify, so we're left with a plausible but unproven hypothesis. The structure might be real, might be plasma, and might be tied to solar wind behavior, or it might be none of those things. This isn't just frustrating for researchers trying to solve the mystery, it's emblematic of a larger problem in citizen science. Amateur astronomers are doing incredible work, generating data that rivals or exceeds professional observations in some cases. But the metadata standards are inconsistent. Some observers record GPS timestamps accurate to the second. Others just write the date in a notebook. Some log atmospheric conditions, telescope settings, and processing steps. Others just post the final image with no context. And when you're trying to do serious analysis, context is everything. The irony is that the smart telescopes generating the controversial images are perfectly capable of recording precise timestamps. The devices have internal clocks synchronized to GPS. The software logs every observation with millisecond accuracy. But that metadata often doesn't make it into the public uploads. It gets stripped out when images are compressed for sharing. It gets lost when files are converted from proprietary formats to standard image formats. And so, the very precision that could resolve the debate gets thrown away in the name of convenience. And that ambiguity is exhausting. Because every time you think you've found an explanation, the data gaps prevent confirmation. Every time you build a hypothesis, the missing pieces keep it speculative. And the longer the speculation goes on without resolution, The more people give up on finding answers and retreat into their preferred narratives. Believers believe, skeptics dismiss, conspiracy theorists conspiracize, and the object itself, silent and distant, keeps moving through space, indifferent to our confusion. It's like trying to solve a jigsaw puzzle when half the pieces are missing, and someone keeps taking pieces from different puzzles and mixing them in. You can see hints of the picture. You can imagine what it might be, but you can't complete it. You can't be certain, and uncertainty, in the age of information overload, is intolerable. People would rather have a wrong answer that feels complete than a right answer that acknowledges gaps. But one thing the solar wind event reminds us is that space is not empty. It's not a vacuum in the colloquial sense. It's full of fields, particles, radiation, and forces that shape how objects appear and behave. And those forces are variable. They change on timescales from seconds to years. So when we ask what 3i Atlas looks like, we have to ask when, and where, and under what conditions, because the object doesn't have a single appearance. It has a range of appearances depending on the environment it's moving through, and that range might be wider than anyone expected. This is a fundamental shift in how we think about celestial objects. We're used to thinking of them as fixed, unchanging. A galaxy looks the same today as it did yesterday as it will tomorrow. But comets are different. They're dynamic. They interact with their environment. And interstellar comets, passing through conditions their materials never evolved to handle, might be even more variable than solar system comets. 3i Atlas isn't just moving through space. It's moving through a changing plasma environment, through varying radiation fields, through fluctuating magnetic pressures. Each of these variables affects how it looks, its brightness, its structure, its emission spectrum. The object is not one thing, it's a process, a continuous interaction between internal composition and external forces, and trying to capture that process in a single image is like trying to photograph a river and claim you've seen water. Which brings us to the final piece of the puzzle, the reminder that the universe still surprises us, that physics is unfinished, that matter can exist in states we're only beginning to understand, and that sometimes the things we call artifacts or anomalies are just reality being more complex than our models allow, which is exactly what happened this year with a breakthrough in our understanding of ice. Yes, ice. And no, this isn't a tangent, because what we learned about ice this year is a perfect metaphor for everything we've been talking about. The solar wind spike of August 2025 might have been the key that unlocked the mystery of 3i Atlas, or it might have been a red herring, a coincidence that led us down the wrong path. Without better data, without precise timestamps, without controlled observations designed to test specific hypotheses, we can't know, and that not knowing is the point, because the universe doesn't organize itself for our convenience. It doesn't wait for us to build the right instruments or ask the right questions. It simply unfolds, indifferent to our confusion, and we either keep up or we fall behind. And right now, with 3i Atlas, we're struggling to keep up. Part 15, the Superionic Ice Breakthrough, 20. 25. Nature still surprises us. Ice is simple. Everyone knows ice. Frozen water, cold, slippery, common. Except ice is not simple. It's one of the most bizarre substances in existence, and the more we study it, the weirder it gets. There are at least 20 known phases of ice, each with different crystal structures, different properties, different behaviours. Some are denser than liquid water, some conduct electricity, some only exist at extreme pressures or temperatures, and this year we discovered a new one that shouldn't exist according to the models we had. Superionic ice. It's a phase where water molecules partially dissociate under pressure. The oxygen atoms lock into a solid crystal lattice, but the hydrogen atoms flow freely like a liquid, or like electrons in a metal. It's solid and liquid at the same time. It's ice that conducts electricity. It exists inside ice giants like Uranus and Neptune, where the pressure is millions of times Earth's atmosphere. At least, that's what we thought. The 2025 breakthrough showed that superionic ice can form at much lower pressures than predicted. Pressures that might exist inside large comets or asteroids. Pressures that might exist inside interstellar objects that formed in cold, dense environments and then got compressed during close passes to stars or planets. If 3i Atlas contains superionic ice, its internal structure could be unlike anything we've studied before, and its behaviour, its reflectance, its emission spectrum could all be anomalous for reasons we're only beginning to understand. The discovery happened in a laboratory at the University of Rochester, where researchers were using diamond anvil cells to squeeze water ice to incredible pressures while bombarding it with laser pulses. They expected to see the transition to supersonic ice happen at around 2 million atmospheres of pressure, consistent with decades of theoretical predictions. Instead, the transition occurred at just under 800,000 atmospheres. That's still enormous pressure by everyday standards, but it's a factor of more than 2 lower than expected. And in planetary science, factors of 2 matter enormously. Why does this matter for objects like 3I Atlas? Because the interior pressure of a large comet or asteroid depends on its size and composition. Traditional models assume these objects are loosely packed rubble piles with relatively low internal pressures. But if an interstellar object formed in a dense molecular cloud and underwent compression during formation or during gravitational interactions with its home star system, it could have retained high-pressure phases of matter in its interior. Supersonic ice wouldn't just be a curiosity, it would fundamentally change how the object conducts heat, how it responds to solar heating, and how it outgasses as it approaches the sun. An object with supersonic ice in its core might have strange thermal properties. Normal ice sublimates predictably when heated, turning directly from solid to gas. But supersonic ice has different thermal conductivity. It might channel heat differently, creating uneven outgassing patterns that don't match standard comet models. It might retain heat longer, or release it in bursts. These behaviors could create the kind of anomalous emission patterns that observers have been reporting: bright spots that appear and disappear, sodium spikes that pulse rather than flow steadily, structural changes that seem to happen too quickly to be explained by simple rotation. But that's speculative, wildly speculative. The point isn't that 3I Atlas is made of supersonic ice. The point is that we keep discovering new phases of matter, new behaviors, new physics, even in substances as mundane as water. And if we're still learning about ice, how can we be confident we understand interstellar objects that formed in environments we've never sampled, under conditions we've never replicated? Consider what else we've learned about ice in just the past decade. Ice 7, a cubic crystalline form that exists at pressures above 20,000 atmospheres, was found naturally occurring inside diamonds that form deep in Earth's mantle. Ice 18, predicted theoretically but only confirmed in 2023, has properties that still puzzle researchers. Each new phase expands our understanding of what water can be and how it behaves under extreme conditions, and water is just one molecule, one simple compound made of the most abundant elements in the universe. Now extrapolate that complexity to an entire interstellar object. An object that formed in a stellar nursery we'll never visit, from materials we've never touched, under physical conditions we can only guess at. An object that spent millions or billions of years in interstellar space, bombarded by cosmic rays, exposed to temperatures near absolute zero, possibly passing through other star systems and experiencing gravitational stresses we can't model. How can we claim to understand such an object when we're still discovering new things about frozen water? The answer is we can't. And maybe that's okay. Maybe the lesson from the entire resolution war, from the instrument debates, from the spectral mismatches and plasma boundaries and conspiracy theories, is that we're not ready to understand 3I Atlas yet. Not because we're not smart enough, but because the tools we have, the models we use, the categories we think in are all optimized for the familiar. For the solar system we grew up in, for the comets and asteroids and planets we've been studying for centuries. Our telescopes were designed to study objects that behave predictably. Our spectroscopes were calibrated for known compositions. Our imaging algorithms were trained on galaxies, nebulae, and solar system bodies. Everything in our observational toolkit assumes a certain baseline of normalcy. We assume objects will reflect sunlight in familiar ways. We assume they'll emit gas through thermal processes we understand. We assume their surfaces and atmospheres will contain materials we've encountered before. And when an object violates those assumptions, our tools struggle. They produce ambiguous data, contradictory images, results that don't make sense. And when something unfamiliar arrives, something interstellar, something that doesn't fit, we fragment it into competing realities. Professionals see a blob because their instruments are tuned for dust. Amateurs see a spindle because their instruments are tuned for light. Conspiracy theorists see a cover-up because institutions won't admit uncertainty, and all of them are partially right and partially wrong, because the object exists in a state of superposition, not quantum but observational. It is what you measure it to be, and what you measure depends on how you measure. That's not mysticism, it's epistemology, the study of how we know what we know. And what 3i Atlas is teaching us, painfully, awkwardly, controversially, is that knowledge is always mediated. There is no view from nowhere. There is no neutral observation. There is only the interaction between the observer and the observed, filtered through instruments that have biases, algorithms that have assumptions, and minds that have expectations. Every observation is an interpretation. Every measurement is a choice about what to measure and what to ignore. Every image is a selection of which wavelengths to capture and which to filter out. And those choices, made for good reasons by skilled people, still shape what we're capable of seeing. They create blind spots. They emphasize certain features while suppressing others. They make some truths visible and others invisible. So maybe the universe isn't hiding anything. Maybe we're just not looking with the right tools. Or maybe we are, and the tools are showing us something real, but we don't have the framework to interpret it yet. Maybe the spindle is plasma. Maybe the blob is nucleus. Maybe both are true. Maybe the object is a hybrid, a transition state, something that exists at the boundary between categories and refuses to be pinned down. And maybe that's the most important discovery of all. Not what 3i Atlas is, but what it reveals about us. About how we see. About what we trust. About how fragile our consensus is when the data doesn't cooperate. About how quickly certainty dissolves into argument when the thing we're looking at doesn't care about our need for answers. The scientific method is supposed to resolve these disputes. You gather data, form hypotheses, test predictions, and converge on truth. But that process assumes the data is clear enough to distinguish between competing hypotheses. When the data itself is ambiguous, when different instruments produce incompatible results, the method stalls. You can't converge on truth when every measurement points in a different direction. You can only wait, gather more data, build better instruments, hope that eventually the picture clarifies. But what if it doesn't? What if some objects are genuinely ambiguous, existing in states that look different depending on how you observe them? What if the resolution war never ends because there's no single resolution to find? That possibility is deeply uncomfortable for science, which is built on the assumption that objective reality exists and can be discovered through careful observation. But objective reality and observable reality might not be the same thing. The map is not the territory, the image is not the object, and when the object is strange enough, the map might need to be redrawn entirely. Because the universe doesn't owe us clarity. It doesn't owe us simple explanations or clean data or objects that fit our models. It simply is in all its layered, ambiguous, contradictory complexity. And if we want to understand it, we have to accept that understanding might mean holding multiple contradictory truths at once. That the blob and the spindle are both real. That the professionals and the amateurs are both seeing something. That the instruments are both revealing and concealing. That reality is not a single story, but a chorus of overlapping narratives, and the truth is somewhere in the harmony if we're willing to listen. And 3i Atlas is still out there, moving through space, glowing or not glowing, structured or shapeless depending on who's watching. And maybe one day we'll know what it is, or maybe we'll just know more precisely what we don't know, and in the end that might be enough. Because the universe is vast and we are small, and the fact that we can see it at all, even imperfectly, even through instruments that lie and algorithms that guess, is a miracle we should never take for granted, even when the images don't match, especially when they don't. Because the contradictions are where the discoveries hide, and the resolution war, for all its chaos and confusion, is just the universe reminding us that we still have so much to learn. The journey from certainty to confusion and back to a deeper understanding is the path all science must walk. 3i Atlas is simply the latest object to drag us along that path, kicking and screaming, whether we're ready or not,